Alright, I hope you guys are doing good. So in the last video, I was showing you how to do the analysis of variance with a single factor, right? You remember that we were comparing the mean of the population of the pigs with 4 different diets, right? And then we were checking whether all the diets have the same effect on the pig's weight or not, okay? So that was an example of the one factor or one way ANOVA. Basically, the reason why we call one way is under the factor diet, there were different groups, right? The diet was the only one factor that you wanted to test for the effect on the pig's weight. So, but one of the main assumptions of the one-way ANOVA or any ANOVA is the equality of the variances. All the variance within the within the different groups must be equal, right? So although testing a hypothesis via ANOVA is okay, so it does okay work if the variances are a little bit different, not very different. But if the variants are a little bit different, when the sample size are equal, the ANOVA works well. But it can give you very misleading results in the presence of serious heterogeneity or of variance. This is of the variance, okay, or unequal sample size. Several approaches. In this situation, there are many methods people use. One of them is the Welch test. So how do we find the test statistic for the Welch test is this. So for the ANOVA, we denote it by F. Here, for the Welch test, we denote by F prime, okay? This is the formula. Summation 1 through K. K is the number of groups or the number of samples. Ci xi bar minus x bar w square over k minus 1 times 1 plus 2a k minus 2 over k square minus 1, where the values of ci, c, all those things are given there, okay? So let us see that. Ci is ni, the sample size, over the variance of that sample. So ni is the number of sample in the number of data in the ith sample divided by the variance on the ith sample. And then big C, we'll use that C later. So big C is sum of those CIs. X bar W is basically, this is the weighted arithmetic mean of the sample means, right? Ci xi bar over C. And A is 1 through K summation 1 minus Ci over C. C is that over Ni square over Ni minus 1. And xi bar is the sample mean, right? Ith sample mean of the ith sample basically. With the degrees of freedom is, for the numerator is k minus 1, and degrees of freedom of the denominator, this is the formula, round to the next lowest integer. We use the same F table as earlier for critical values, and for p values we use FCDF, or do you remember we use PF, or you can use QF for the critical value, okay? For PF you use so for the p value you use PF, okay? So a modified version of the Welch test is basically Brown and Forsyth, also used with the test value F double prime, group SS, group sum of square divided by the B, where sum of square is given by this value, and B is given by sum of 1 through K BI, where BI is 1 minus, and I is the sample of number of data in the ith sample, and divided by the total data times SI squared, with degrees of freedom is given by for the numerator and denominator. So these are the formula you use for the Welch test, meaning if you are doing the ANOVA, but if the variance are not equal, then this is the method we use. Let's see one example there. So the potassium content per 100 gram of plant tissue was measured in 5 seedlings of each of 3 varieties of wheat. So variety G, variety A, variety L. Okay, these are the data points. You see that. So 1, 2, 3, 4, 5, 6, right? So each of them have the sample size 6. Use alpha equals to 0.05 to test whether the mean potassium content is the same for seedlings for all 3 wheat varieties. Assume that the variances of the potassium content are not equal. We are assuming that they are not equal. They may be equal, we haven't checked, but we want to do using the Welch test, assuming that the variance are not equal. Okay. So the H0 and H1 are all of them have the equal equal average on the potassium content, and H1 is the mean potassium content is not the same for seedlings of all 3 wheat varieties. The general mean of all data x bar gm is 35.5. So sample size, sample mean, sample variance, CI, we use that formula for the CI. So CI is, if you remember that, Ni over Si square, right? So Ni over this divide that, this divide that, this divide that, that is the Si square. That is the, so Ni over Si square, this divided by this divided by that one. So basically, let me circle that. This is basically the CI, and CI times Xi bar is this 26 times 0.46. These two, product of those two will give you CI times Xi bar. Okay, and then you plug in those values. 1 minus CI divided by C square over Ni minus 1. This is what you get for. So what is CI? CI is given by this one, right? So you do 1 minus CI, you find out the sum of those, that the sum of those CI is 21.4215. You plug in here and then divide by Ni minus 1. If you use that, you will get these values, where C is that value, X bar W is CI Xi bar over C. This is the weighted mean, basically. This is what you get. And then, so this is what you get, okay? That is the X bar W. Thus the test statistic, if you use the formula above, this is what you get. Test statistic is 17.5. You see that? Okay, the critical value or the p-value. For critical value, we use F table. Okay, so what is our alpha? Alpha is 0.05, right? So you can use R to find out the critical value. So what is the critical value then? Critical value is, you can use QF, right? What is alpha? Alpha is 0.05. That is on the right side, right? Because we use the right tail test. So what is the left area? Because for the R, you need the left area. Left area is 0.95, and then degrees of freedom of the numerator is 2, and degrees of freedom of the denominator is 9. If you do this, you will get the critical number as 4.26, right? If you use the p-value method, then p-value will be, you do PF, right? And then you do 1 minus PF. It is similar to the Anova, 1 minus PF, and then 17.5, and then 2, and then 9. If you do that, you will get 0.0007. So since the test statistic F falls in the critical region, why? Because your critical value was 4.26, your test statistic is 17.5, right? So it is, which is bigger. That's why it falls in the critical region, right? So we reject the H0. What is happening there is your critical value is here. So 4.26. Anything that falls right side of this will reject the null hypothesis. But our F prime falls somewhere here, right? So we reject the null hypothesis. So there are not enough evidence. We reject the null hypothesis. So, or in other way, it is p-value is less than alpha, right? So we reject H0. So there are not evidence that the potassium content are same among the 3 varieties. So let's do the exactly the same problem using R. Okay. This is, you can see this is the R code. We have the I have uploaded this code in the Georgia view. Okay. Let us do this exact same example using R. Okay. So using, if you want to do by hand, you can do it, but it is a lot of work. So what I'm going to do is I'm copying these data points in R, variety G, variety A, variety L. I will do V1, V2, V3, and then copy those. Okay. So let us do that. So V1 is that data, V2 is that data, and V3 is that data. So what I'm trying to do here is I'm trying to put these data into the two columns. Okay, the first column is those numbers and second column is the varieties. Okay, so groupings basically. So the 27.9 is V1, 27 is V2, so we will write that way. Okay, V1, so 27.9 V1, 27 V1, 26 V1, and so on. So we want to write that form as in the previous example. So let me run those, and then I am doing that. So how does that look like? You see that? This is what this look like. So the potassium content and the variety. So you see that up to here is a variety 1. That's the first 6 data points. Similarly the other one. Now, so now I want to, we are already assuming that the variance of the populations are not equal, but just curious whether they are equal or not. What I'm trying to do is I'm trying to check homogeneity of the variance. How do I do that? First of all, I will run the Anova test and then find the summary. I mean, I don't need to find the summary of the Anova test because this is not what we are trying to do, because this Anova test assumes that the variances are equal. Okay, but we will test it with this. It will be easier, otherwise you will have to find out check the variance separately. Okay, so here what I'm trying to do here is I ran the Anova test. Now what I want to do is I want to use the Lebanese test to check whether the variances are equal or not. What does it give you is the p-value is 0.0089. Alright, since the p-value is less than alpha, so we reject the null hypothesis. What was our null hypothesis? Our null hypothesis was variance are equal, right? And the alternative is variance are not equal. So we see that variance are not equal. Okay, so these data have the unequal variances. So we don't use the analysis of variance there. What we do is we use the analysis of variance with the assumption that the variance are not equal. So variance equals to false. You see that? So now if we run this, what you get is basically not assuming the variances are equal. Okay, so this is the Welch test basically, and then what you get is the F value is 15.01. okay, and the degrees of freedom of the numerator is 2, degrees of freedom of the denominator is 9.2. so we get very close to what we got in the slide. Okay, and the p-value is 0.0012, which is also very much similar to the value we got. So basically we reject the null hypothesis. What does that mean? That means that the potassium content, because p-value is less than alpha, we reject the null hypothesis. So the potassium content on those 3 varieties of the wheat are not equal. That's what we can conclude from here. Okay, so the next thing we want to do is we want to discuss which ANOVA to use, where to use which ANOVA. Okay, let me read those points. There are several methods for comparisons of the mean of more than 2 samples. When you write a research report, you should mention which procedures were used for any statistical analysis. When comparing means, you should report sample size, the sample average, and the sample variances or the standard deviation of each sample. The following are the general guidelines to pick a method. Okay, if K samples populations are normally distributed, okay, or approximately normally distributed and have identical or nearly identical variance, then we use ANOVA. In that case, we use ANOVA. Okay, so if all the population are normal or close to normal, and if their variances are equal or close to equal, then we use ANOVA. This is best method. Note that if the p-value associated with the F test is very near to alpha, you should be more careful while interpreting the result. If possible, okay, you should repeat the experiment for more data in such situation. If the population is slightly non-normal, then the ANOVA we discussed is still valid if the sample sizes are equal. Or if the sample size are not equal but the sample sizes are large, you are still okay. And if the variances are equal, you are still okay if you are slightly deviated from the normal. Okay. If the variances of K population are not equal, the ANOVA we discussed above is still valid if the sample sizes are equal. That's what it says. If K sample population are normally distributed, but they have very dissimilar variances, you can still use ANOVA to compare K means. If extremely high or low means are associated with the small variances, use Welch test. And if extreme means are associated with the large variances, you can use Brown and Forsyth test. If the K sample population are very different from normal distribution, but they have similar distribution and variances, okay, they are very different from the normal distribution, but they have the similar, both of them have the similar distribution. Although they are not normal, they are the similar distribution. And if they have the similar variances, then Kruskal-Wallis test. You remember that? So this is a non-parametric test, right? Kruskal-Wallis test is used. Okay. The next is, if the K sample population have distributions greatly different from normal and do not have similar distribution and variances, consider transforming the data to other distribution which will be a normal and homogeneous variances. Sometimes we do not perform hypothesis testing and just report the mean and variance of the K samples if that happens. Okay. If outliers are causing non-normality or heterogeneity of variance, you can correct the data. If you think the data is incorrectly reported, like using different units or missing decimals or decimals in wrong place, you can correct them. In other cases, you can use non-parametric tests that do not require any of those assumptions, normality assumptions. Okay, so these are the homework problem. These problems are due on next Monday. Okay guys, so complete these problems using R. Okay, so the last thing that I wanted to discuss here in the in this video is Kruskal-Wallis test. We remember that we just discussed about the non-parametric test, which is the Kruskal-Wallis test. So if a set of data is collected according to completely randomized design where there are more than 2 samples, it is possible to compare them non-parametrically for difference among groups. Non-parametric tests are desirable if the K samples do not come from normal population. Okay, if the population are not normal, then we usually use the non-parametric. If very normal, then if the population are not normal or deviated from normality very much, then we use the non-parametric test. It also works well if the population have slightly different dispersions and shape. So there are several methods for comparison of populations using non-parametric test. Kruskal-Wallis test, also called the analysis of variance by ranks, is one of the best, which almost as powerful as parametric ANOVA, using the test statistics F in any situation where the F test is applicable, and in fact more powerful in the cases where F test is not applicable. So if the F test is applicable, then both of them will give you similar result. And sometimes if F test is not applicable, meaning if the variances are very unequal, or if the population is very non-normal and the sample size are not equal, in those situations F test is not applicable. So in that case, this Kruskal-Wallis test is applicable. As in the parametric ANOVA, Kruskal-Wallis test tend to be more powerful with a larger sample size, and the power is less when the sample size are not equal, especially if the large means are associated with the small size sample. Okay, it performs well if the total sample data exceeds 20. So if the total n is the summation of the total sample sizes of the different samples, or the total data points is bigger than 20, this is okay to apply. If there are just 2 samples, the Kruskal-Wallis test is equivalent to the Mann-Whitney test. Note that both tests do not test whether the means or medians are different from each other, but instead address whether the sample population have different distribution or not. Okay. However, if the steps are similar, then the test becomes the test of central tendency. With Kruskal-Wallis test, the type 1 error is less affected with the heterogeneous variance than the parametric ANOVA if the group with large variance have small sample size. So these are the steps. I think we discussed these steps in the previous slide too, previous video too. So this is the formula to find out the test statistic. R1, R2, R3 are the sum of the ranks in each of those groups. N1, N2, N3 are the sample size, right? N is the total sample, and Ni is the so N is the total sample. Ri is the sum of the ranks in the ith data of the sample, right? Because what we do in this case is we collect all the data in one place and then rank them first, and then add the rank of each of those groups for R1 to find out R1, R2. Okay. In case of the tied ranks, the test statistic is H sub C is equals to H over C, where C is calculated by this formula. Ti is the number of ties in ith tied rank. M is the total number of tied rank. Okay. Critical value for K is less or equals to 5, mean if there are 5 or less samples, we use Kruskal-Wallis H distribution table with N1, N2, N3 degrees of freedom. Those are the degrees of freedom for each of those. And then for K is greater than 5, we use chi-square test with K minus 1 degrees of freedom. Okay, if the test statistics fall in the critical region, reject H0, otherwise do not reject H0. If you want to use p-value method, find the area right to the H. Reject H0 if P is less than alpha. So basically we are using the right tail chi-square test in the case of K is greater than 5, right? So these are the examples I did here. Okay, the slide is posted already in GeorgeV, so you can look at the examples, but I am doing this problem using R. This has tied ranks. Okay, this example has tied ranks, so more complicated than the first example. So what I'm going to do here is I am going to show you how to use R for this problem. You see that? Non-parametric alternative for one-way ANOVA, example from the slide. Okay, so let me run these data points, point 1, point 2, and point 3, and I want to write into the 2 columns. You see that? So these are the 2 columns. These are the I think the phosphorus content in point 1, point 2, point 3, and point 4. So these are the pH level in point 1, point 2, point 3, point 4. So these are the values. You see that there are these values are from the point 1 and the other are point 2 and point 3, point 4, like that. Okay, so what I'm going to do next is I want to see how does the bar plot look like. It looks like the point 4, you see that point 4 have the higher median or higher average, right? You can see that. Now what I'm going to do here is I am going to do the ANOVA here. Okay guys, so if I do the ANOVA, because I want to test whether the variances are equal or not, okay, whether the normality assumption is valid in this problem or not. That's why I want to do the ANOVA first. If I do ANOVA, what do I get? Is I see that with the ANOVA test, I see that the p-value is less than alpha, meaning that the mean pH level in those points are not equal. Okay guys, so let us do the homogeneity of the variance. If I do the homogeneity of variance, this is the plot. Okay, we cannot say for sure from the plot. We see that this line, the solid line, is almost overlapping the dotted line, but statistically it doesn't say anything, right? So what I'm to do is I want to use the Leibniz test. You see that when I do the Leibniz test, it says that the variance are not equal. Okay, the variance are not equal, and I try to use another test for the equality of the variance, which is the Fligner test. If I do the Fligner test, this also give you the p-value is less than alpha, so the variance are not equal here. Okay, so it violates. I did not test the normality, so since the variance are not equal, so one of the method give you very small p-value. So it looks like the variance is variances are very heterogeneous. So what I'm going to do next is I want to use the non-parametric test, that is the Kruskal-Wallis test. If I do the Kruskal-Wallis test, I got p-value still less than alpha, so meaning that the pH level in those ponds are not equal, right? Now there is an alternative way you can test. You can use the Kruskal-Wallis test. You can do Kruskal test, and you don't have to do pH level and then that curly sign and then pond. What you do is you can do list and then pond 1, pond 2, pond 3, pond 4. What it does is it compares the median of these values, okay, or yeah, central values you would say of these 4 groups. Okay guys, so this is what we got. Now there is one more example I have taken. Let's see the air quality example. So under the library card, I'm taking data 1 is equals to air quality. I did the box plot. Okay, so what I did is I did the month ozone level versus the month. So I wanted to see whether the central values, central or the average ozone layer for each month are equal or not on the air quality data. Okay, what I did is I first wanted to check the analysis of variance, whether the mean are equal or not, but I'm not interested on that. What I want to do is I want to check the normality. The normality is, it says the data is not normal, its p-value is less than alpha. So it may be because of these, there are some outliers, or it may be the data are like that. I am not interested to check that right now. What I'm to do is I would use the Kruskal-Wallis because the normality is violated, right? So the data is not normal at all. So the Kruskal-Wallis test gives me that the p-value is less than alpha, meaning the average value of the ozone per month compared to each month are not equal. Okay guys, that's all. Thank you.